At first glance, this looks like it would benefit from either a displacement or velocity time graph. So just having a quick look through, there's acceleration here, so I think a velocity time graph would be the most appropriate. So I'm just going to draw out a graph here and then sketch the parts of the graph as I read through the question. A train moves along a straight horizontal track, so let's just put V and T there, between two stations R and S. Initially the train is at rest at R, so that would be here. The train accelerates uniformly at 0.5 meter per second squared from rest until it's moving with a speed of 15. So let's mark 15 on here. And now I'm going to show that the gradient of that is approximately 0.5. Doesn't have to be exact, it's just a sketch. For the next 200 seconds, the train maintains a constant speed of 15. So that will be going along here. And I'm just going to divide that up so we can mark those values on the time axis. The train then decelerates uniformly at 0.25 meter per second squared until it comes to rest at S. So this is going to be a slightly less steep gradient. So it's worth just writing on m equals 0.5 and m equals -0.25, and then I don't have to go back to the question. This distance it said was 200, at the time it said was 200 seconds, so that's from here to here. I don't know the time here, so I'm just going to mark that as T1, so time 1, time 2 and time 3. And I think I've got everything marked on the graph there. Find the time taken by the train to travel from R to S. So I need to find these two times here and here. I have initial velocity, final velocity, and so I can, and acceleration, so I can use V equals U plus a t for each of these. So final velocity for the first part of the journey will be 15. Its initial velocity is 0 and the acceleration is 0.5 t. So that gives me a time of, rearranging that, a time of 30. For the second part of the journey, we've already got that, time is 200 seconds. And for the third part of the journey, final velocity is 0, initial velocity is 15 up here, and it's -0.25, the acceleration, and then t, so t is equal to 60. And altogether that gives me 290 seconds. For part B, we have to find the distance from R to S, and on a velocity time graph, the distance is the area under the graph. So either by splitting it into 3 different areas, calculating their areas and adding them together, or just by using the area of a trapezium, we can calculate that distance. So I'm going to use the area of a trapezium. The top is 200. The base we've worked out in part A of 290. So 200 plus 290 divided by 2 multiplied by the height, which is 15. And that gives me 3,675 meters, or 3.675 kilometers. For part C, the average speed of the train during the journey from R to S. So average speed is total distance over total time. So average speed, total distance is 3,675. Total time taken, we've worked out here 290. So the average speed is 12.7 meters per second. Now, marks wise, there's a method mark for using V equals, clear use of V equals U plus AT either here or here, and an accuracy mark for working out either the 30 or the 60 correctly. Then there's another accuracy mark for adding those three up for getting 290. For part 2, there's a method mark for clearly calculating by dividing into 3 areas or by using the area of the trapezium with the value that you found from part 1. There are 2 accuracy marks and 1 is lost for each mistake. And then there's an accuracy mark for 3, 6, 7, 5 and that. And then for the last part, a method mark for using your distance divided by your time, and an accuracy mark for 12.7.